So what we did last time is we just introduced the concept of Turing machines. And towards the end, we noticed this cool fact, that there are certain functions from natural numbers to natural numbers which are not Turing computable. Let me first say what it is for a function to be computable by a Turing machine. So say you have a function f from the natural numbers to the natural numbers. So in other words, for each natural number, the function outputs a natural number. So one way in which you could get a Turing machine to compute this would be to design it so that whenever it starts with a sequence of n ones on the tape and nothing else, and let's assume the reader at the position of the first one of that sequence, the machine works and halts and leaves an output of f of n ones. So that's what it would be for a Turing machine to compute that function. And similarly, if you have an n-place function, so a function that takes n numbers and delivers a number of output, you could get a Turing machine to compute it by having it start with a sequence of sequences of ones separated by spaces, and then make sure that whenever you start the machine with that input, again with the reader position at the very start, it's going to work and halt. And you're going to end up with a sequence of ones, which is as many as it's going to be m ones, where m is the result of applying the function to your input. So that's what it is for a Turing machine to compute a function. And now, yesterday we saw that there is a very quick proof that not every function of this kind is Turing computable. And it's just to do with cardinality reasons. So it's just to do with the fact that there are not enough Turing machines. So let's verify that now properly, like last time. OK. So first, who can give me a quick proof that there are as many, or there are at least as many functions of this kind as there are real numbers? And it's OK to use results that we proved in previous sessions.
So you can consider all the functions that go from the natural numbers to the set 0, 1, and then those are like the first one is like 0, 0, 0. The next one, like they're basically just all the binary, infinite length binary strings. And
that's exactly right. So a subclass of these functions, as you pointed out, are the functions that go from natural numbers to the set 0, 1. Which are just sequences of zeros and ones with one position in the sequence for each natural number. And that's just the kind of beast that we saw has the same cardinality as real numbers. So since that includes all of these guys, the set of functions of this kind has to be at least as big as the real numbers. OK. And now what about the set of all Turing machines? So can anyone think of a proof that there are only countably many of those? And a crucial observation here is going to be that every Turing machine has a finite program. It has finitely many states. OK, so here's one way to do it. So what I did here is I wrote down a partial list of all possible command lines that a one-state Turing machine could include. And it's just all possible combinations. So this one says, if you're in state 0 and you find a blank, leave a blank, stay put, and stay in state 0. And that one says, if you're in state 0 and find a blank, write a 1, stay put, and go to state 1. And of course, because there is no state 1 in a one-state Turing machine, that means halt. And I basically wrote them all, except that I need one more column of this kind for go left and one for go right. So if I'd written 3 columns like this one, but just varying what the action is, then that would have been an exhaustive list of possible command lines for one-state Turing machines. This, by the way, presupposes that we're working with one symbol in addition to blanks. Otherwise, we would have had to have more combinations about what you can write down and more combinations about what you can find. The crucial observation is that there are just finitely many of these, which means that if you look at all possible one-state Turing machines, there are also going to be finitely many of those, because you know, all you're going to do is to build a one-state Turing machine is pick 2 of those. One that tells you what to do if you're in state 0 and find a blank, and one that tells you what to do if you're in state 0 and find a 1. So that's it. And something similar is going to happen for Turing machines with 2 states. So again, we're going to have a finite list of possible command lines, and you're going to pick 4 from those. You're going to pick, at most 4. You're going to pick one that tells you what to do if you're in state 0 and find a blank, what to do if you're in state 0, find a 1, what to do if you're state 1, find a blank, what to do if you're in state 1 and find a 1. And again, you're going to build them from combinations of those. So you're going to have finitely many possible 2-state machines. And similarly for every n. So here's a way of showing that there are countably many in total. We can number them. So we can assign a natural number to each Turing machine. Just let 0 be the first one on our list of 0-state Turing machines, and count them all until we get to some number k. And then let k plus 1 be the first of your 1-state Turing machines, and count them all until we get to some number j. And then let j plus 1 be the first of your 2-state Turing machines, and so forth. And every Turing machine is going to be assigned some natural number. So there are as many Turing machines as natural numbers. So we know that there are functions that are not Turing computable. And here's what's exciting about this. As I pointed out last time, there are the functions that are Turing computable are exactly the same ones that are computable by an ordinary computer. Indeed, an ordinary computer with unlimited memory. So that means that there are functions that no computer of the kind we know and love could possibly compute. And you know, that is a very deep fact about computers. They're limited in this essential way. And notice that that's in spite of the fact that we're not here talking about efficiency. So we haven't talked about functions that could be computed quickly. Like, things are going to get much worse if we do that. Here's just things that can be computable simpliciter. OK, so what I want to do today is give you guys an example of a function that's not Turing computable. So some of you might have heard of it already, especially those of you in course 6. But the whole thing is so beautiful that if you're like me, you'll like just going through it anyway. OK, so the function that we're going to show is not Turing computable, is the halting function. And here's how it works. We are going to give the halting function two numbers. And it is going to deliver 1 as an output if the nth Turing machine halts an input k. And it's going to be 0 otherwise. So what do we mean by the nth Turing machine? Well, that is relative to some way of ordering Turing machines, such as the one I gestured to here. there are many, many ways of doing it. The nicest one that I know of is in the lecture notes. But I'm not going to do it today because it would take a long time. So here we have a function from pairs of natural numbers to natural numbers. And what we're going to do is we're going to show that this function is not Turing computable. Everyone good? So the way the proof is going to work is we're going to assume that the Turing function is computable. Sorry, the halting function is computable. So that means that we have a program. It might be very long, but it's finite. And it delivers that result. And once we have that program, then we know that we can use it as a subroutine to construct other programs. And we're going to see that if we indeed had it as a subroutine, then we could do impossible things. So it cannot be a subroutine, so it cannot be a program, so the halting function is not Turing computable. One way of imagining this is if it were computable, then you would have like this machine such that you can give it two numbers and it outputs a 0 or a 1, the halting function. And you could connect that machine to other machines to do weird things. And what we're going to see is that if you connect it to other machines in the right kind of way, then you would be able to produce something impossible. OK, so here is our impossible machine. I'm going to call it the evil machine. So the evil machine takes one input. So take input, which is a string of k ones. And then the first thing that it does is create a copy of that string right next to the original one with a blank in between. So if we give the evil machine a sequence of 5 ones, it's going to start with the reader there, and then it's going to do some stuff. And after a while, it's going to end up with a second sequence of 5 ones. And we even know how to do it. I mean, it's a slight variation of something we did on Monday. OK, and then the second thing it's going to do, and this is the crucial step, is that it's going to deploy the program of the halting function as a subroutine. Because remember what the program of the halting function does. What you do is you give it two numbers, and it outputs a 1 or a 0, depending on whether the Turing machine corresponding to the first number will halt given the input specified by the second number. So what's going to happen is that when we apply the subroutine to this, it's going to be like asking the question, does the fifth Turing machine halt given input 5? So then what's going to happen after we do that? In fact, maybe I'll write all steps. Is that we're either going to get a 1 or a blank. We're going to get a 1 if kth Turing machine halts on input k, and we're going to get a blank otherwise. OK, and now comes the evil part. If you get a 1, then what our machine does is it goes on a never halting task. So for example, it just goes right forever. And we know how to do that too. And if you get a 0, what it does is halt. So in other words, it does the opposite of the output it got. If the output it got is the kth machine halts on input k, it never halts. And if it says that machine never halts, then it immediately halts. OK, so we have our evil machine program. And because our evil machine is, we're assuming, a Turing machine, it has its number in our canonical numbering. Let's say that it's the ETH number. So then consider the question of what happens when you input E to the evil Turing machine. And what's going to happen is that it's going to ask the question of whether the ETH Turing machine halts given input E. In other words, it's going to ask the question whether it itself halts given the input you actually gave it. If the answer is yes, it's never going to halt. If the answer is no, then it's going to halt immediately. So in other words, it's going to do the opposite of what the halting function says that it itself should do. And that's impossible. So there can be no halting machine. What could be more beautiful than that? I mean, one thing that's fabulous about this is not just that it's remarkable that the function wouldn't be computable. It's also remarkable how easy it is to prove that it's not. Yes?
I sort of have a problem with this weird numbering all of the Turing machines, and that's set and determined, and I don't know, why can we do that, and how could a, even like in this theoretical argument, how can we use that as that is one of the inputs into the Turing machine as the number of which Turing machine it is referring to?
Good. So that's fair enough. So let me talk about that in a little further detail. So first, let me just notice that this is an issue that the evil machine doesn't have to deal with. Because think of things just from the point of view of the evil machine. So the evil machine doesn't really care what number you give it. So you just give it a number, it duplicates it, it asks the halting machine a question, and depending on the output of the halting machine, it does something. So this is not really an issue for the evil machine. Of course, in order for the whole setup to make sense, then we need to know how the numbering works. But here's one way in which you can think about the numbering, and this is the method that I use in the lecture notes. The first observation is that you can think of each command line of a Turing machine as just a sequence of 5 numbers. Now, it's true that the way one normally writes it, not everything is a number. We have, for example, blanks and letters there, but that's very easily corrected. So let's use the following codes. So code blank as 0, right as 0, left as 1, stay as 2. So using that coding system, every single member of our command line is just going to be a number. So that means that a command line is just 5 numbers. So maybe it's 0, 1, 0, 0, 2. And now we can make use of a very cool fact about arithmetic. I think this was discovered by Gödel, the same guy who proved the theorem we're aiming for. And it's that because of the fundamental theorem of arithmetic, because every number has a unique decomposition into primes. Yes?
So you can use this system to give every Turing machine a unique number, but then, it's arguable whether that's ordering them or not. Because they'll each have a unique number, but then still, how could that be an argument into a Turing machine?
Oh, right, OK. There is actually something quite important in what you're saying. Let me say a little bit more about this just to make sure that everyone is on board. And then I'm going to come back to what you're saying, because it's important. OK, so a command line is just a sequence of numbers. And you can encode a sequence of numbers as a single number, but just doing this. So let these numbers be A, B, C, D, and E, and take this number, 2 to the A plus 1 times 3 to the B plus 1 times 5 to the C plus 1 times 7 to the D plus 1 times 11 to the E plus 1. So I just picked the first 5 primes. This product is just going to be a number. And because of the fundamental theorem of arithmetic, if you're given a number, you can easily determine whether it came from a product of this kind. And if so, what A, B, C, D, and E are. So you can very easily use natural number to extract a sequence of 5 numbers. And of course, one can generalize that trick, because you can think of a Turing machine program as just a sequence of these guys. So in other words, it's just a longer sequence. And by choosing a longer sequence of primes, you can code those. So in other words, if you're handed a number, one can easily compute the problem of whether it comes from a product of this kind. In fact, the only thing you have to worry about is that there are no gaps, because every number it can be decomposed into primes. And if it does, you can easily determine what the exponents are. And so you can easily determine what your sequence of numbers is. OK. So what we have so far, yes?
Are you saying that if you get a really big number, you can factor it in such a way that you can recover what every line of code? Because that doesn't... Well, but how could you tell which line... like, it seems like you would get some prime factorization, but how do you know which ones belong to the first line of code and which ones belong to the second line of code?
No, that's a good question, but it sounds like you want to offer an answer. Yeah.
So the trick to that is you get these large numbers that represent one line of code, and then those large numbers go into the exponents of another set of primes that represents your whole program. So to fully get a program back from some huge number, you'd factor that number, you'd look at the 2 exponent, the exponent of 2 of that number. The exponent of 2 of that number is the first line of your program. So then you do that prime trick again to get the individual parts of the first line of your program. Then the exponent of 3 of your huge number is, again, going to be one of these that's on the board, and you can break that up to get line 2 of your program, and so on.
OK, so if you have however many lines of code you have is however many primes you go out to.
Good. So that is definitely one way of doing it. So on this way of doing it, what happens is, suppose that you have 44 lines of code. Then what you do is you pick the first 44 primes, and you just look at the exponents, subtract 1, and that's going to give you a bunch of numbers. And then for each of those numbers, you see whether they can be decomposed in this way. And then you look at the exponents and subtract 1, and then you get the numbers. So that's one way of doing it. Another way of doing it, I mean, they're both equivalent, is you just use the fact that every command line consists of exactly 5 symbols. And then you just put them one after the other. And however many numbers you get, you consider that many primes. And you multiply to get the number. And if someone gives you the number, then you just factor it. You get the exponents. You use them to just write like this long sequence of numbers. And you know that the first 5 are going to correspond to the first command line, to the next 5 to the next one, the next 5 to the next one, the next 5 to the next one. OK. So now finally back to your question. So a crucial feature of this numbering system, this coding system, is that it's not just that it gives each Turing program a code. It's also that it does so in such a way that can be processed by Turing machines. Because this kind of operation is exactly the kind of things that Turing machines can do. So you can easily program a Turing machine so that if you give it a number, it factors it into primes. And you can easily program a Turing machine such that given a prime factorization, it determines what the exponents are. And then you can easily program one that subtracts 1 from all of those. And then you can easily program one that creates a sequence using those. Contrast that with a different case, and this is why I think your question is so deep. Suppose that I say, no, I'm going to just use my the following weird numbering device. I'm going to use a numbering device that assigns odd numbers to Turing machines that halt and even numbers to Turing machines that don't halt. That can be done. It's just that it's a coding scheme that, as it were, Turing machines can't understand. Because in order for a Turing machine to do something useful with the number you get it needs to be able to process it. And because Turing machines can't compute the halting function, the coding scheme that I just described is one that they would not be able to do anything with. You give them the numbers, but they would be stuck. OK, so I think the answer to your question is that it's not just that we can assign a number to each Turing machine. It's not just that we can assign a code to each Turing machine. It's that we can do so in such a way that Turing machines can work with. Let me make a parenthesis to mention an amazing fact about Turing machines. Even though the halting function is not Turing computable, something that is Turing computable is the universal function. The function that takes you from a Turing machine and an input to the output that that Turing machine would have given the given input. And what happens if the relevant Turing machine doesn't halt given that input? Then the function is undefined. So in other words, there is such a thing as a universal Turing machine. There's a Turing machine that given a code for a Turing machine and a number works and works and works and works and delivers the same output as that Turing machine given that input. And should that Turing machine given that input not halt, then the universal Turing machine just keeps on going forever.
I would like to see the code for the Turing machine that can simulate a different Turing machine.
It would be very long, but one thing we can do is I can try to give you a little additional detail about how it works. So how to build a universal Turing machine. So it takes as input mk. So in other words, a sequence of m1s followed by a sequence of k1s. And informally, what's going to happen is that the machine is going to treat m as a code for a Turing machine and k as the input that that Turing machine is meant to compute. So the first thing it needs to do is unpack m. So this is all relative to the coding scheme. If the coding scheme we're using is this one, then the first thing that our universal Turing machine does is it starts factoring m, and using either of the methods we described, ends up with a bunch of numbers which correspond to the program. And then it just writes down the program on the tape. And then the second thing it does is, so unpack m to get a copy of the program on the tape. And then the next thing it does is write down a reader state indicator. And here's what I mean by that. So here's a tape, and you just start with a sequence of M1s, and then a space, and a sequence of K1s. So the first thing that happens is M gets unpacked. And that huge beast just codes the program of the mth Turing machine. And then you have your K1s here. One thing one can do is one can insert an indicator in here that encodes information about where the reader is and what state it's in. So here's a way of doing it if we have symbols other than 0 and 1. So you can just have a bunch of things and then say x, 5, x, and then a bunch of things. And we interpret that to mean that the reader is positioned at the third one, and the machine is in state 5. And how do we do this if we only have one symbol? Well, you use the trick that we described last time. So what you do is you think of ones as taken in groups, and you take each group to code like one symbol of your multi-symbol machine. OK, so what happens here? So at this point, we have basically a complete representation of a Turing machine at a given state written down on our tape. So the next thing we do is start simulating. So we get our universal Turing machine to go to the reader and see what state it's in. We assume that it starts in state 0 and say, OK, state 0, so let me go back to my program and see what to do in state 0, given what I'm reading. And then figure out what to do, and then go back and do it, and then see what the new state is and what symbol it's reading, and go back and check what to do, and go and do it, and so forth. Now, in order to be able to carry that out, it's going to have a buffer somewhere on the tape to keep track of what it's doing. But that can be done. I mean, one way to do it is, again, in our many symbol system, is you could just have, say, buffer starts notation, and then a bunch of stuff here, which are just its notes. So then, it just does things like it reads 5, so then it enters a certain kind of state and goes to the buffer and says, OK, what do I do with a 5? And says, OK, go check one little thing. And it goes check the little thing and comes back and says, OK, this is what I found. What do I do next? And so forth. And spelling that out is cumbersome, but that's something that can be done. When I was in college, I attempted to do this in full, and it was a very long process. OK, so that's a universal Turing machine.
Can you feed it a universal Turing machine?
Yes, you can. So what would happen if we feed a universal Turing machine a universal Turing machine?
I mean, that would work, right? I assume that you could continuously do infinite loops as long as at the end, the infinite Turing machine has an actual thing that it's going to solve. Because if you just fed it the Turing machine, it wouldn't do anything. But you need some solution for it. It would just take longer.
That's right. It would just take longer. The reason that I wanted us to talk about the universal Turing machine is because it gives us a hint about how one might prove the important theorem that I mentioned last time. The theorem that the things that a Turing machine can do are exactly the things that an ordinary computer can do. Because we use the same trick. So what you do to show that everything an ordinary computer can do is that you find a Turing machine that simulates an ordinary computer. So in order to do that, you need a very abstract description of an ordinary computer. And the way people normally do it is by thinking of it as a finite register machine. So it's basically you have a finite number of buckets, and in each bucket you can put a number. And then there's certain basic operations that the computer can perform to do with what's in each bucket. So it can say, well, go to bucket 17. If you find a 3, then add 1 to whatever is in bucket 44. And you guys can imagine how a Turing machine might imitate that. It just has sections of the tape that correspond to each bucket, and then whenever it's asked to do things, it laboriously imitates whatever the other machine would do. And how do you go the other direction? How do you show that everything that a Turing machine can do, an ordinary computer can do? Well, you simulate a Turing machine in an ordinary machine. And in fact, we saw a simulator yesterday that does just that. So simulation is a powerful trick. OK, so here's what's going to happen next. One of my favorite thinkers alive today is an MIT computer scientist called Scott Aaronson. You're going to see him, and you're not going to believe that someone that young could be so amazing. And he's agreed to come on Monday, and I think basically just talk to us about whatever we want. I think what will be most interesting to talk to him about is things to do with efficiency. So we're no longer worrying about these cases where a Turing machine can simply not compute something. Now we're worried about whether it can compute it relatively quickly. And a special case of this is, something closely related to this is the issue of quantum computation. So it turns out that if you have some particles and they are entangled in the quantum sense, then you can create a different kind of computer, a computer that operates with different rules. And it's not the case that a quantum computer can compute functions that no Turing computer can compute. They can compute the same functions. But a quantum computer can do certain things much more efficiently. In particular, it can factor primes very, very efficiently. That was also proved by an MIT professor, though a different one. And that makes all the difference because, for example, most of the world's encryption is based on the assumption that a computer cannot factor primes quickly. So in effect, the way it works is you just have a very large number, and if you know how it was built, then you can just use that information to decompose it and extract information. But if you don't know how it was built from primes, then it would just take too long to factor it, and it would take too long to be able to extract any useful information from it. But if you have a quantum computer, then you can basically break every code of that kind. And like there'll be a disaster much bigger than the one that was caused yesterday when it was revealed that SSL is in fact unsafe. So hopefully he'll talk to us about that. Now, there was something that I wasn't sure I would have enough time to talk about today. And in fact, I don't have enough time. That's the busy beaver function, which is super cool. It's another example of a non-computable function. And it's especially interesting because the proof that it's not computable is like a baby version of the proof of Gödel's theorem. So like I want to make sure that we have proper time to do it. So what I'm going to do is, Scott is coming on Monday. We'll talk about the busy beaver function on Wednesday. And good news for you guys. I'll change the deadline for this week's problem set to next week. So basically, no problem set this week. Same problem set that's already online will be due next week. Because the point of that problem set is to get you guys to understand the busy beaver function. So yes, oh, poor, you all must be so busy. You all look so happy. So don't miss Monday because it'll be really cool to have Scott.